Hello, everybody. Well, we're getting towards the end of the unit packet, so this will be the last video going over this procedure on how we determine the molecular shapes of simple molecules. So, in summary, the protocol or the rules to determine the shape of molecules is first you determine the two-dimensional shape of the molecule based on the formula, the molecular formula using the Lewis dot diagram procedure. Once you have the Lewis dot diagram of the molecule, you look at the central atom and you count the number of places where electrons are located. Once you know this number, then you can use the VSEPR table to determine the shape. So why don't we do a couple of these problems? We'll go over the procedure again. Okay, here's a couple of problems. Let's try this one right here, SnCl3. So Sn is 10, and Cl is chlorine. But there's three of them. Notice that there's three of them. So there's tri for 3, chloride. We always end it in ide. Okay, I wonder if I can erase this. I just need a little bit more room. Okay, so we have 10 in the molecular formula, and we have chlorine, right? SnCl3 minus. Okay. So the next step, we have to figure out how many valence electrons or outer electrons there are in each of these atoms. To do that, we have to go to the periodic table. So I'm going to go to our periodic table. Here we are. Now I need to look for 10. Here's 10 right here, 10, and chlorine right here. Okay, now notice that 10 is in column 14. 14, right? Here's the little 14. And then chlorine is in column 17, right here. Okay, these column numbers help you determine the number of valence electrons. All you have to do is subtract 10. So 14 minus 10 is 4. 17 minus 10 is 7. So we know that 10 has 4 valence electrons, and chlorine has 7 valence electrons. But notice that there's 3 chlorines. So I have to multiply by 3, the 7 times 3. And in total, we have 7 times 3 is 21, plus 4 is 25. Okay, let me erase that. Let me put that the way it's supposed to be. But notice, in this molecule, there's a negative charge. Now, to account for that negative charge, the fact that this formula has a negative charge, I have to add an electron. It has an extra negative charge, so I have to add 1 to the number of electrons. So in total, we have 26 electrons. Okay, So the next step, we have to use the Lewis dot structure to determine the two-dimensional shape of this molecule. So what I'm going to do is I'm going to take the first atom and I'm going to put it in the center. Then you're going to use single bonds to predict the shape of this. I'm going to add the chlorines using single bonds, and it really doesn't matter where you put them, but just remember there's a top, a bottom, and a left and a right. So why don't I put one over here? And it's really up to you. You can put them anywhere you want, as long as it's top, bottom, left, or right. I'll put one down here, and I'll put one up here. I'm going to get rid of that. Why don't I get rid of that just to make it cleaner? Okay, so the fact that I used 3 single bonds means that I used 6 electrons because each single bond is 2 electrons. So I have to subtract 6 from my total, and I've got 20 left. Also notice that these electrons, they always come in pairs. Oops, sorry. Okay, so I've got 20 electrons. Now I have to stabilize each atom in this molecule. Now remember, there is a rule where atoms need 8 electrons in order to be stable. So I will put 2 there, 2 there, bottom, 2 on the right. Okay, so now that chlorine is stable. Let's do it to this one too. 1, 2, 3, 4, 5, 6. Now that chlorine is stable because it's got 3 lone pairs, 2 each, and the single bond, 2 more. That's 8. Try there, 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 and there. That's 6 more that I've used up. So in total, to stabilize these chlorines, I've used 18. Notice that I have 2 left. Now, notice that the 10 in the center, it still needs 2 more. So I'll put them there, and there we go. And we're done. Now, the last thing I want you to do is I want you to put brackets around the structure and put a little negative sign here just to let people know that it has a negative charge. Okay, the next thing we do, we have to determine the shape drawing. The shape drawing is determined using the VSEPR table. But before I show you the VSEPR table, first you count places where electrons hang out in the molecule. Okay, so notice there's a single bond here, right? You're counting where electrons hang out around the central atom. There's a place right here. There's a place right here. There's 3 single bonds, and then there's a place right here where there's a double, where there's an electron pair. So that's 4 places. 1, 2, 3, 4. Okay, now we can go to our VSEPR table. Here it is. Okay, 4 places. So here are your choices right there. Those are your choices. Okay, these are places where electrons are found around the central atom. Okay, now out of these places, how many are bonding? Well, we had 3 single bonds, and how many are lone pairs? 1. So here is our structure, and here's a shape drawing. So let's go back and finish this off. Okay, so trigonal pyramidal. And the shape is, we got 10 in the center. And then we have a chlorine up here, a chlorine down here, and a chlorine down here. This is like a flat triangle. So if I made the shape of a triangle here, and because it is a triangle, we know that the angle between each of the chlorines coming off of the tin is 120 degrees. Okay, I am gonna go to the last page. So let's see if we can do this problem right here. We're gonna use the choices below to indicate the value closest to the true value closest to the true value for the bond angles represented in the following structures. So how do we do that? So first we're going to look at this carbon right here, angle A. It's between these two hydrogens. Okay, so let me draw that out here. Basically we have a hydrogen up here, a hydrogen there, a hydrogen there, and then it's connected to another carbon. So the question is, what is this angle right here? Well, we use our VSEPR table. So we have a carbon, and how many places do electrons hang out around this carbon? One, 2, 3, 4. 4 places. So let's go to our VSEPR table. Again, we're looking at 4 places where the electrons hang out around the central atom. And of these 4 places, how many are bonding and how many are non-bonding? Well, in this case, all 4 are bonding. So in this case, we have a tetrahedral. So if we were to draw the shape drawing, we would have the carbon in the center. We'd have a hydrogen on top. We'd have a hydrogen down on there, and notice that these lines here, they indicate that the hydrogens are in the plane of the paper. And then we'd have a hydrogen coming out of the plane of the paper, indicated by a wedge, and then we'd have this carbon here would go back into the plane of the paper, indicated by a dash. Okay, this is called tetrahedral. And the angle between the ligands, we call them, these outer atoms, the angle is 109 degrees. So the angle for A is 109 degrees. 0.5 degrees. Okay, what about this next one here? What about this one right here, angle B? So in this case, we have a well, why don't we get rid of this? Well, no, I'll leave it there. In this case, we have a carbon bonded with another carbon over here. And it's bonded to a hydrogen, and then we have a double bond right there to the nitrogen. Okay, so how many places do you find electrons around this central atom? We're interested in this angle right here. Okay, count the number of places you find electrons around the central atom, which is 1, 2, 3 cases. We got 2 single bonds and a double bond. Go to your table. Okay, now we're interested in the number 3. We find electrons around the central atom in 3 places. Of those 3 places, how many are bonding places? Well, all 3 are bonding, and there are no lone pairs. So we have trigonal planar. Okay, so in this case, I'll try to write it down here. We're going to have the carbon in the center. We'll have a carbon on top, a carbon down there, and then we'll have the nitrogen, and then we have the rest of the molecule. This angle here, because it's trigonal planar, it's in the same plane, is 120 degrees. 120 degrees, 120 degrees, 120 degrees equals 360. So that's 120 degrees. Okay, if you guys, I know I'm erasing this, but you can always back up the video and, find out and write down what I'm erasing. Okay, what about the last one? What about C? C right here. So here we have an oxygen. Oops. We have an oxygen. We have a double bond there. We have a hydrogen over here. We have another, I didn't say double bond, I meant lone pair. We have a lone pair on the bottom of the oxygen, a lone pair on top. And then we have a nitrogen with a single bond over there. Okay. Again, count the places where electrons are found around the central atom. And here we have 2 single bonds. And then we have a lone pair on top and a lone pair on the bottom. That's 4. Okay, again, we're down here with 4 places. Okay, of those places, how many are bonding? Well, 2 of them, 2 single bonds. And how many are non-bonding? 2 lone pairs. So in this case, the angle is bent. So I'm going to draw it like this. I've got the oxygen. Okay, so I'm going to put a nitrogen down here in the plane of the paper. And then I'll put the hydrogen down here also in the plane of the paper. Coming out of the plane of the paper, I've got 1 lone pair of electrons, and then going back into the plane of paper, I've got the other lone pair. Okay, and this is called bent. And the angle between the nitrogen and the hydrogen is 109.5 degrees. Okay, well, that's it for today. And I will be putting out information in the next few days, later today or the next few days, how we're going to assess your understanding. In other words, how are we going to determine how well you know about the learning goals of covalent bonding? So I'll put out that information, and we'll figure out how we're gonna do a quiz on this material. Okay, I hope your day's going well. I'll see you next time. Bye-bye.